This is the notes video for section 2.5, slides 24 through 27. The topic of section 2.5 is differentiability. So let's read this. It says, if f prime exists, we say that f is differentiable at x. So differentiability is, well, the existence of the derivative, right? So what does this mean in terms of limits? Remember, we defined the derivative as a limit. So remember, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Remember, this is the derivative at x. All right, but now we recall back from Unit 1 that in order for the limit to exist, the right hand and left hand limits must exist and be equal. So that means that the limit as h approaches 0 from the left must equal the limit as h approaches 0 from the right. So what does that really mean? All right, so let's go ahead and take a look at a similar drawing to what we did before. All right, so let's say that we have this point here. And this is just some f of x point, right? So it's x comma f of x. All right, now you could put some other value over here, right? Which is a certain distance h away, right? Now that means that this point is x plus h comma f of x plus h. Now, when we did this initially, we put that point over there, right? But it could very easily be that this point was over here, right? So this could be x plus h comma f of x plus h as well. But if it were over here, then that would mean that in this case, h is negative, right? So that means h is approaching 0, but from the left. Over here, if that x plus h point was on the right, that would mean that h were approaching 0 from the right. So what we're saying is, if the slope of the tangent line, so let's make sure we draw that in, if the slope of the tangent line is to exist, then that means the slope of the secant from the right must be approaching the same value as the slope of the secant from the left. So that's all that we're really saying. All right, so what we need to do is we need to make sure the derivative on the left of a particular value is the same as the derivative on the right of a particular value. So now, differentiability is just like continuity. What does that mean? Well, in order for the function to be differentiable, it must first be continuous. All right, so if we say, when is a function differentiable, the first thing we need to consider is, when is it continuous? If it's not continuous there, then it cannot be differentiable there. All right, so moving on to slide number 25. Okay, graphically. Okay, when will a function not be differentiable? Well, there are basically 5 ways that a function is not going to be differentiable. All right, so the first one is called a corner point. So we see this here. All right, this is just kind of a sharp turn in the graph. Now, this graph specifically would be f of x equals the absolute value of x. All right, so I'll talk a little bit more about that, but basically there's a sharp turn. All right, a cusp looks very similar, right? Kind of a sharp turn, but the difference is that these derivatives are approaching an infinite value, whereas with a corner point, they are finite values. They just happen to be different. All right, now this function here is actually f of x equals x to the 2/3 power. So we'll talk a little bit more about that. All right, the next one, vertical tangent. All right, so now there is not a sharp turn, but the tangent line is vertical, meaning its slope is undefined. All right, this function is actually f of x equals x to the 1/3 power, or the cube root of x. All right, number 4, this one's really easy. Any discontinuity. This one happens to be a jump discontinuity, but if it were an infinite discontinuity or oscillating discontinuity or removable discontinuity, all of those are situations where the function will not be differentiable. So remember, like I said a moment ago, all right, the first thing we consider when we're considering differentiability is continuity. All right. All right. And then lastly, number 5, an endpoint. An endpoint. So a graph that we had a couple times show up in Unit 1 was like the square root function, right? So if I have the square root of x, or x to the 1/2 power, right? It is undefined at its endpoint. Sorry, the derivative is undefined, meaning it is not differentiable. Okay, so now why are these not differentiable at those points? All right, so first of all, let's take f of x equals the absolute value of x. All right, so f of x, well, this is actually just a piecewise function. On the right side, this is y equals x, and on the left side, this is y equals negative x. So the question is what is f prime as we approach 0 from the left? Okay, please understand that notation. What is f prime on the left side? Well, it's negative 1. But what is f prime on the right side? Well, it's positive 1. These two things are not equal, therefore the function is not differentiable. All right, what about number 2? Well, let's think about f prime. All right, f prime of x, that would be very simple, 2/3 x to the negative 1/3, right? In other words, this is 2 over 3 times the third root of x. So now let's think about f prime of 0. Well, f prime of 0, that would be 2 over 3 times the third root of 0. Third root of 0 is 0. 3 times 0 is 0. So this is 2 over 0. This is undefined. So we say f is not differentiable at x equals 0 because f prime is undefined. All right, what about vertical tangent? Well, basically the same thing. F prime of x equals 1/3 x to the negative 2/3. All right, and so once again, f prime of 0 then, well, think about that. That would be 1 over 3 times the third root of 0 squared, right? But of course, 0 squared is 0. Third root of 0 is 0. 3 times 0 is 0. So once again, we get 1 over 0. So that is undefined. All right, therefore, the function is not differentiable. All right, obviously, any discontinuity, we already talked about that. All right, what about an endpoint? Well, in this scenario, it's pretty easy to show that f prime of x, well, what would the derivative of the square root of x be? That would be 1/2 x to the negative 1/2. So just like these other ones, 1/2 x to the negative 1/2, well, f prime of 0 would be 1 over 2 root 0, right? Well, that's 1 over 0 once again, and so that is undefined. But to broaden this, okay, any endpoint is not going to be differentiable, okay? All right, so moving on to slide number 26. All right, so slide number 26 says, show that f of x is not differentiable at 1, 0. All right, so first of all, is the function continuous at 1, 0? Well, the answer is yes. I mean, you can see that, but let's say that this were presented as a piecewise function, right? This piecewise function would look as follows. X squared minus 2x plus 1, and that is when x is less than or equal to 1, and then y equals 2x minus 2 when x is greater than 1. All right, so now, okay, we want to think about, okay, well, what is the derivative on the left side? So I'm going to take f prime of x. All right, so f prime of x. Well, what's the derivative of x squared minus 2x plus 1? That's 2x minus 2. All right, what is the derivative of 2x minus 2? That is 2. Right, so the derivative on the left would be when x is less than 1, and the derivative on the right is when x is greater than 1. Now, ask yourself this. Is f prime of 1 from the left equal to f prime of 1 from the right? So, that's a question. All right, so now, what is f prime of 1 from the left? So that means put 1 into the top piece. 2 times 1 minus 2. That would be 0. Equals 2. That is not true. Therefore, f is not differentiable at 1, 0. All right? So that's how we consider differentiability. Okay? All right. So lastly, slide number 27. All right, I have this graph. All right, so at what domain values does f appear to be differentiable? All right, so first of all, let's consider differentiability cannot occur, right, at an endpoint. So right away, the endpoints, -4 and +4, are not going to be included. All right, so then we want to look for corner points, cusps, vertical tangents, and or lack of continuity, right? All right, so we have right here at -2, we have a corner point, right? See how that's kind of a sharp turn? It is not smooth there. All right. Then at 0, we have a jump discontinuity. Then moving on, this is smooth, smooth, smooth. And then at 3, we have a removable discontinuity, right? So what does that mean? At every other location other than those ones I named, it is differentiable. So that would mean from -4 to -2, right? From -2 to 0, from 0 to 3, and then from 3 to 4, right? So we're talking about differentiability upon an interval of values from x equals -4 to -2, from x equals -2 to 0, from x equals 0 to 3, and then from 3 to 4. All right. When is it continuous but not differentiable? So basically, okay, we are trying to name places where it was continuous, right? But not differentiable. So we have -4 at the endpoint. All right. So it is continuous because it goes up to that endpoint and it is a closed circle. So we would say -4, comma. It is continuous at -2. It is not continuous at 0, and it is not continuous at 3, but it is continuous at the endpoint. Now, when is it neither continuous nor differentiable? So that is when it does not have continuity. So that would be at 0 and 3. Okay, now the other possibility, okay, A, B, or C. Well, what about D? Differentiable but not continuous. Well, that's not possible because it can't be differentiable if it is not continuous. So that is not a question that we ask.